Okay. Hello, everyone. My name is Jan. Welcome to our podcast, CG Papers and Chill. Today I'm with Barney and Alessandra. And yeah, how are you guys? Nice to see you again.
Nice to
Right.
see you. Good to be here.
Yeah,
Right.
absolutely.
Yeah, the first session I was with Barney and we talked about differentiable rendering and cloud rendering paper, which was really interesting. And we were missing a lot of people, actually still miss a lot of people, but at least we have Alessandra with us today.
Gradually,
And she
we're
was
getting more
also,
Yes.
yeah,
one by one.
Alessandra was also one of the participants in the Central European Seminar of Computer Graphics in Smolenice, a student seminar. She also presented her paper, so hopefully in the future she will also talk about her paper, maybe. Let's
True,
see.
yeah.
Let's see
We'll have to do
if we
that.
can, yeah. Let's see if we can keep this podcast going. But I'm motivated.
I mean, we're getting more people now, right? So
Right.
Yes,
Yeah,
absolutely.
it's looking
Nice
really
linear
positive.
curve that we have going
yeah.
on.
At least no one's leaving yet, so that's good.
Yes. That's true.
Right. Okay, compared to the previous session, this is going to be rather different, I think, because last time we had a session where we really into the discussion and we kind of felt like that might not be possible for the future events. So our thought was to make it more of a podcast, rather informal friends having a nice conversation about maybe computer graphics and more basic stuff. So in today's episode, I'm basically gonna talk about physics-based differentiable rendering, an introduction, which was a course in 2020 SIGGRAPH. But we will definitely not going to talk about all the details, not only because it's not a complete paper, it's rather course notes, a collection of course notes. But as well, there is a great amount of material from, especially a video that you can watch, the listener can watch. So it probably makes more sense if you watch the video and maybe watch this podcast episode to maybe see the different ideas that we kind of inferred after reading the papers. Okay, so
Yeah, so we are keeping the sense of reading papers and then chilling together. So nothing changed in that regard. But yeah, at the same time, we are trying to get it to the best possible form for a podcast.
do you guys want to say anything before I start? Should we begin with the toy questions that we
Yeah,
had?
absolutely.
I just wanted to say
So
that, yeah.
to keep in line with the absolutely. So to keep in line with the whole podcast
Right.
concept, we were just thinking about like chatting a bit about relatively unrelated topics that are still keeping in line with the main idea of chilling with graphics papers. So yeah, we were thinking about each of us will ask a question from the others and then have a little discussion at the beginning of the podcast, and we will see how
Do
it
you,
goes.
any of you have prepared any questions? I didn't.
I did.
But I
Yes,
can
of
find
course,
good
of
spontaneous
course.
questions. Okay, that's
Yes.
good. That's good. Then you guys can start because I need to think about it in the meantime.
Do you want to start, Barney?
Oh no, you can go ahead.
Okay.
He's also thinking maybe like, oh.
Okay, so my question for you is, I don't even think that we've talked about that. Maybe I don't remember it. Anyway, my question is, why did you get into computer graphics? What was the motivation behind it, or was there a specific reason? Games.
Actually, not
random
games
choice?
for me. Actually, not games for me.
Okay. For me neither, because I feel
So
like that's a big point for a lot of people.
Mm. You want to answer first?
Yeah, sure. I
Because
can go ahead. I can go
yeah,
ahead. Yeah, it's. I think this could be like a whole podcast episode in itself because this is such an
That's what I was
exciting
actually
thing
thinking.
to be excited about computer graphics and what drew you in and stuff.
You're
But
like, well, let me
actually,
start.
yeah, yes, let me start. Yeah, but yeah, for me, this really started like really early. It like really liking animated movies and animated pictures, and you know, you have like your traditional animation with you know, you have a board with some light inside it or underneath this like a glass, and then you know, like traditional animators used to have these like multiple papers stacked over each other, and they would animate by hand each frame. And I was just so amazed by that. And I was also attending these like as a kid. I was attending like these weekend camp, so to say, or like these little activities where you were. Yeah, so we were in one of the animation studios in Hungary, because we used to have like a lot of these animated or like multiple really cool animated studios, and they organized these weekend activities for children, and that was so cool. And I even had my own board at home and everything.
Cool.
So
Oh.
yeah, sadly I didn't stuck with it for long enough. But then I also went to like multiple summer camps on this topic with like animating little things. With so I really came in from the animated movie direction, and then of course like I saw the Pixar movies, and that it's possible to, I don't know, write some mathematical formula that will then animate hair, for example, or the ocean, or I don't know, like that's just so cool. And yeah, so I really came in from the animated storytelling and animated movies direction.
So do you have any background in animation, in the sense like also art side of the animation? Can you draw
No,
like
I've been practicing and I've been trying to, but it's not really something I like developed enough to make it worthwhile. But at the same time, like I love it. I think it's just so amazing to like tell these stories with through art. And I also did like theater play, so maybe it's kind of intertwined with like storytelling and doing drama school and stuff like that. So I really like, to me it's all about storytelling and how you can tell these amazing stories with these awesome technical tools. And yeah, you know, like I think Pixar sums it up really nicely. The art challenges technology, and the technology inspires art. So for me, it's really all about that.
That's nice. That's a really good
so
story.
impressive what they do in Pixar. Yeah.
What about you, Chan? What got you into computer graphics?
Oh, that's a really, this could also be another podcast episode, but whatever. So, like when I first came to Vienna, I actually wanted to study psychology, and I entered this study examination, and there were, I think, 5,000 people, because it's so popular to study psychology in Vienna. Who knows why? Freud maybe, but I failed miserably. Like from 4,000 people, I think I was like 3,800 or something like that. And my second choice then was studying computer science, just because I was playing video games a lot, and I was relatively good at it, but like on really simple tasks. And then I started studying computer science, just hoping to do something visual, but kind of hit the console window of the computer, and you just learn this abstract stuff when you first start programming, like write I don't know, stupid tasks about dividing numbers so that you can get a stupid console log message. It was so hard to understand that, but eventually, anyways, I found my way to computer graphics, and I kind of find the whole idea of computer graphics, creating something visual, much more intuitive, rather than maybe working on something really abstract in mathematical sense. but not just that, because something can be mathematically, something can be abstract in mathematical way, but if you can put that into a visual medium, it just becomes, it's then easy to understand. But if you can't really visualize it in high dimension, that just for me really difficult. So it's kind of a inevitable evolutionary consequence of my stupidity, maybe. That's why I basically study computer graphics.
Evolutionary result of my
stupidity.
I think I didn't expect that answer, but that's really awesome. Yeah, I think that's really cool. It's also really interesting when you just look at these little tutorials that these computer graphics kind of oriented programming languages have, or visual programming languages have, or even like libraries that are about computer graphics have like these little intros. And for example, like just Daichi, which is like a programming language targeting high performance computing and computer graphics and stuff. Like for example, one of their tutorials is just like a couple of lines that animates a Julia set, for example. It's like swirls and rotates and animates, and then some other packages or tutorials that have, I don't know, like some fluid simulation example or something like that, or little ray tracing example or something like that. So I think that's really nice, much nicer than, I don't know, targeting some, I don't know, inventory management software, or I don't know.
Yeah, definitely agree. Is it also like that for you guys? Is it easier to understand something visually, or do you have a visual intelligence, let's call it that way, or rather more abstract understanding?
No, I think for me it's definitely visual. And that's also why I like it, that you have a visual output. Because
Right.
I just enjoy it more, you know.
I absolutely agree. Like, yeah. So I think that's really nice when you can like animate and plot what changes if you change this or this number. So I think like some illustration or animation really goes a long way. But at the same time, I also learned that sometimes it's really nice and beautiful to just put down an equation, for example, and have a way of grasping some underlying thing about something that you do or you're interested in through some equation. So I think that's really nice and powerful too. But yeah, I'm also much more for having a really nice illustration most of the time.
To me, it was like with rendering equation, just I don't know, something changed in me in a way, like, because it is rather a complicated equation. When you look at it first, it's actually not that complicated, but when you understand it, the rendering equation, it's so intuitive. Like, we will talk about this maybe in coming paper. So
Yeah. I think you also mentioned this during the previous podcast, that it's so nice that you can like pinpoint stuff in the equation. Okay, this is the photons, I don't know, being occluded, or this is the, I don't know, the shadow part, or this is like what happens when photons bounce into, I don't know, material particles or something. That's really nice, and you like integrate over the unit sphere around all possible incoming ray directions and stuff. So that's true. It's really cool. It's nice.
I also feel like I really enjoyed
physical.
Yeah, exactly. I really enjoy this part of physics, right? So like optics and I don't know, reflections, stuff like that. So yeah.
Yeah, that's true. And Alessandra?
Yeah, what about you?
There's not really. I think your stories are much more interesting. For me, it was like, so I did my my bachelor studies in biomedical engineering, and I wasn't 100% happy with it. There was something missing, but I didn't know what yet. And then I discovered, I actually really like programming, and I'm going to focus more on that. And then I kind of tried to find a way, like, how to do that, because I was like stuck in this biomedical engineering bubble. And I think we just had one, what's it called? Like compulsory elective courses or something like this. It's called like that. We had like a catalog of courses,
that you can choose,
and we had to choose a certain amount. Yeah, exactly. And I think there was computer graphics and vision 1, also 2. And I just signed up for it because I was like, yeah, why not? Let's have a look at it. And then I was like, oh, this is really cool. This would be a way to combine biomedical engineering with like programming a bit more, because it does make sense, you know, there's the whole like computer vision stuff with like medical imaging and everything. So yeah, and then I decided, no, I'm gonna go fully, or I'm gonna do a bit more of computer science, and then that's why I'm doing my master's now in information computer engineering.
Information computer engineering. Okay. Do you guys also have visual computing at Technical University of Graz?
Only as majors. Yeah, so that's my major in information computer engineering. I think you can also choose that major if you're doing computer science. Yeah, maybe even something else. I don't know. So that's my way. It was more like just trying something out because of why not? And then being like, oh, wait, this is really cool. I discovered something here.
Yeah.
And I also remembered maybe I was a bit. One more thing happened why I stuck with it then, because I also did my bachelor thesis in computer graphics, and the reason because of that, or the reason why I did that, was that at the computer graphics and vision 1 course, in the end they told us like, oh, we have this program where you can write the bachelor thesis at our institute, and you can also apply for getting like an internship where they pay you at the institute to do that. And I was like, wow, why not try that? So I didn't get the internship, but I still wrote my bachelor thesis.
That's how they get
institute.
you.
Yeah. But
it was a really nice prelude to your work. Like if at one point we get around to talking about your work that you presented at CES, what John also hinted at, then that was a really nice prelude
Money
to that.
was the reason behind it.
Yes, money was the reason. That's so nice, yeah.
No, yeah. So I wasn't disappointed for too long. Yeah. In the end, I really discovered something interesting. Yeah.
So you felt something was missing, and it turned out that it was computer graphics all along.
Yes, that was the secret.
Yes.
Because we had like some courses, and I really enjoyed that. But yeah. Was not enough.
That's kind of life, isn't it? Like it just for me, it also works like that. Sometimes I don't really have a specific plan. At least I didn't have any specific plan until like last 2 years or whatever. I kind of find computer vision and computer graphics, and then I realized, wow, this is actually really cool, and I would really like to get better at it. Like that was actually the motivation, and before that it was kind of a really fuzzy, just I'm doing this and I understand it, but it's not really that interesting. Computer graphics and like computer vision and astronomy, like also astronomy plays a huge role for me, because especially the astrophotography part where you just photograph, and in astronomy you actually kind of really use the digital image processing skills. So that kind of pushed me, my interest in astronomy kind of pushed me to the, to that direction of computer graphics or computer vision. And it was just kind of random, but that's kind of, I guess.
That's so cool. Yeah, I remember seeing some of your astro photos that you showed us. Yeah, those are really cool and beautiful.
Yeah, thank you.
They really are.
I really wanted to do more photos, but couldn't really. I don't know, when you start to work, because someone needs to pay for the rent, it's so difficult to go out like middle of the night to just take some photographs of the stars. But that, yeah,
that's quite poetic.
Okay, it's Barney's turn then.
Yeah, sure. Yeah, absolutely. So the question I wanted to ask you is that whether you remember, can you pinpoint the first paper that you read, or the first computer graphics paper, if it differs the two?
That's a good question. I can start. I know already, but
okay. Then I'm going to think a bit more. No, please start.
I don't really remember the name of the paper, but It was so great. It's also actually related to astronomy in a way, so that's actually why I'm remembering it probably. It was a human-computer interaction course in the University of Vienna, and we got this paper about a museum where they kind of digitized the museum, and they were kind of researching how humans interact with the digitized version of the museum, and the museum was actually about astronomy and how they present data, for example, the data they had, etc. And that kind of sticks to me to this day. And it was so much fun to read that paper. And I just find, oh man, I wish I could do something in the future like this, because I don't really care about maybe like software engineering details that I'm doing at work, but this kind of stuff would be really cool, like working for a museum and doing astronomy related, but also maybe visual related stuff. And doing that academically is just sounded really incredible, and that kind of pushed me to read more.
It sounds so
That's
interesting,
really cool.
actually. That's such a good idea.
I'm gonna find the paper name, by the way, but you guys can.
Okay. I
In the
really,
meantime, talk.
I really don't remember the first computer graphics paper that I read. It was probably something for my bachelor thesis, because before my bachelor thesis, I only did like the introduction courses. So I don't think there was any need to read papers or something. So, but I remember in the biomedical engineering studies, we had to do like a seminar at one point, and I actually had such an interesting topic, which was so random. It was about early detection of tooth decay.
Really?
And that
Wow.
was surprisingly interesting. They did like different like methods, like I don't know, shining some type of different light on teeth, and you can detect the stage of decay depending on, I don't know, how the light reflects or interacts with the tissue or something. But yeah,
That sounds really cool.
that was like such a niche topic, but it was so interesting. And then, yeah,
It's really cool.
I don't remember a lot, but back then I had so many unnecessary fun facts about tooth decay and related topics.
Yeah, when
like
you go to social
party
events, you
topic.
just suddenly, exactly.
That's cool.
Yeah.
That's cool.
What about you,
Anyway,
Barney?
I found the paper.
Oh.
Sorry.
Yeah. So yeah. Oh yeah, John, you can go ahead. Did you find the paper?
Yeah, I'm just gonna show the paper just really quickly, if I can manage to share my screen.
Yeah, we will overlay it for the podcast.
Right.
So here.
It's called You Scientist, Designing for People Powered in Research in Museums. Really huge props to the people who wrote this paper. It really is a cool read, and it's about basically human-computer interaction in a museum, and they have key conclusions as well. So I don't really remember. I read this paper 2 years ago. It was really fun to read. Anyways, yeah.
That's really cool. Yeah, it's really cool.
The authors are called Obiora and his colleagues, You Scientists Designing for People-Powered Research in Museums.
Yeah,
So
sounds cool.
congrats to them. Okay.
Yeah.
That's
They wrote
pretty much it.
the first paper that John can pinpoint that you had. That's cool. Yeah,
What about you, Barney?
Yeah. So for me, have you seen the series Pixar in a Box on Khan Academy?
No.
Actually,
I know Khan Academy, but
you
I
know
don't
Khan
really
Academy?
know that.
Yeah. So it's kind of like 3 blue, 1 brown on like
okay.
lots of. Actually, like the person behind 3 blue, 1 brown. Actually, I think did some lectures with Khan Academy. Like, but it's kind of like
Cool.
but it's around a lot of topics on physics, maths, computer science, how to start your life, and like it's really cool. So it's really a nice kind of so it covers a whole wide range of topics, but what's relevant for this my first paper is that they also have a collaboration with Pixar, which is called Pixar in a Box, and they actually go through lots of topics in computer graphics. So actually, like, they literally go through all of the pipeline of computer graphics, from like coming up with a story, developing your characters, then animation, simulation, rendering, I don't know, everything. Like, it's so cool. It's really cool. And they actually do these little mini interviews with people from Pixar, like researchers and technical directors and everything, and they talk about their corner of computer graphics, so to say, and also their background and how did they get involved in computer graphics. So, like, if I could single-handedly point everyone interested in computer graphics towards one resource, and I actually do this when someone asks me like how to get started into computer graphics, it's that series of little topics. And so what really got me hooked for the first time was the hair rendering part. So they had this hair rendering paper, which was I think the name of the paper was Simulation of Curly Hair. So that was actually developed for the movie Brave.
Yeah, I remember
by
that
Pixar.
book.
So the main protagonist had this curly hair, which was like hard to simulate, and that was like the first magical interaction for me with computer graphics. And like I just wrote, and I actually ended up implementing that for some mandatory electives.
Really?
Individual research kind of topic. So that's why I dive deeper into that. But it was just so cool that there are like people from Pixar actually talking about what they do and how they develop these movies and the technology behind them. And they actually had a paper that was like a proper paper. So it wasn't just an interview, so to say, but it was like a whole, and they also had these little JavaScript snippets that you could run on the web, and like they literally had like interactive little exercises online for this course that you could develop.
Cool.
Sounds really
yeah, and
cool,
then I went ahead and played around a bit with this paper, but I think that was the first paper I read from beginning to end properly, and like going after the literature that they cited and everything. So I think that was the first one for me.
That's really cool. When you talk
so
about
cool.
mention, yeah.
I mean, really looks interesting.
Yeah. I kind of vaguely remember doing some stuff from Khan Academy about computer graphics. It's probably what you mentioned, because I remember I was kind of stuck with an assignment and kind of found a link from Khan Academy. They were kind of talking about really initial ideas, and I think I know what you mean. Yeah, sounds definitely really cool.
Yeah. It's I think that is one of the coolest things on the internet ever. I mean, that's just it's really.
I'm really gonna check it out.
We are so lucky. Like, trying to learn computer graphics 40, 50 years ago would have been really difficult. I was talking with a colleague the other day. I think she's rather a senior developer, and she mentioned that she finished her studies in 80s at Technical University of Vienna, and she mentioned the computer graphics was the coolest stuff that you could have studied, but nobody could really show you anything. It was just more theoretical than it is today, and it just changed crazily. Like when you think about the technology that we have right now.
Yeah, absolutely. Yeah. So it really goes hand in hand with the crazy hardware developments that we had going on. So yeah, I remember reading Jos Stam's in Jos Stam's book on fluid simulation, that he was the first one to show real-time fluid simulation, I think, and he presented it at one of the SIGGRAPHs. I can't remember which one, 80s or 90s, and it's so crazy that like anything can run like a all right looking fluid simulation nowadays. It's something you can find on Khan Academy, and you can run it in your browser or on your mobile phone. Yeah, that's absolutely, I think we don't give enough credit for that, and just like how mind-blowing that is.
Yeah.
It's really funny. Maybe we should cap these questions on like one or two sentence, answers. Oh yeah, I didn't mean it to cap it before you ask your question, but yeah, I was just thinking about.
I was just thinking about that as well, and I wanted to ask: should I ask my question, or should should we actually continue with the paper? Which one is more fun to you? I kind of know the answer, but
Both of them are really fun. So I mean, like differentiable rendering is really a really cool topic. So
okay, we can maybe do it this way. I can maybe roughly talk about differentiable rendering a bit, and then stop and then ask my question in the end.
Okay. Stop for
it's like a treat.
So we have something to look forward to then.
Yes,
exactly. Yeah.
Yes, that's true. Yeah, that's cool. Please.
Okay, just trying to find my notes. Let me just increase the size because I actually wanted to. Maybe this is probably the best way to.
Yeah. So just to recap, our current plan is to have John like tell us like an overview of the course notes, so what it contains and what are some really interesting ideas or aspects that we can talk about or develop a discussion around.
Right, exactly.
Yeah, and what the whole differential rendering is about. So this is the intro to our topic.
I have some notes before I actually wanted to talk about it. So the first thing is to you guys, actually. Just interrupt me whenever you can because I don't really see your face. I don't really have any visual cue whatsoever. So just interrupt me whenever you guys want.
Okay.
And the second thing, so this is for other people, basically. If you're interested in differentiable rendering but never read or heard anything about it, this is probably not the best way to start. So this discussion is going to be really an overview, really.
So you mean our discussion? So you don't mean the tutorial, but you mean our paper? You mean our podcast? Our
discussion,
right now.
Like this podcast is probably the worst way to start. But
I mean, I would like to debate that actually. So I think being excited about something is really preliminary to actually getting started with the thing. So if you don't have the motivations to start it, then you will never finish it because
It's a good point.
You actually are
on marketing. That's a good point.
But yeah, if you have a test tomorrow on physics-based differentiable rendering, then maybe our discussion is not the best point.
We should have said it in the beginning, not now.
Right. Yeah. Basically, we're gonna we will give an overview, but if you are really interested in the material, definitely check out the material provided by Zhao and his colleagues. And also for the recent developments, check out Wenzel Jakob and his colleagues, what they do. It's really phenomenal. Okay, that was the first thing that I wanted to say. The second thing is, so basically we are not experts in these topics as well. So we are students too. And the main goal of this podcast, essentially to motivate one another to read more papers, right? So if you are an expert and somehow landed in this strange episode, feel free to correct us either through comments or email or whatever you like, and feel free to provide us some material so that we can mention or maybe spread them as well. So okay, that's the second thing that I want to say. And the third thing that I want to say is, so this article that we're gonna really roughly talk about is rather a long one, and it is probably, and it's not really feasible really to talk about it in one go. Even the course itself is 2.5 hours long, and like doing that course is in one go is also not possible, as I did that course like a couple of times.
Yeah, I can vouch for that too. So it's not really a one sitting kind of deal.
Yeah, exactly. Yeah, basically I'm gonna jump a lot of sections to let me note that, especially when we have some mathematical background or examples. Not because only mathematical ideas are difficult to discuss, especially in a podcast format, but myself as well, I'm not really that confident enough maybe to discuss them really right in front. Another thing, so that's actually kind of important topic, I think, generally about reading papers. And I had a professor 2 years ago, professor from University of Vienna, Moritz Grosse-Wendrup. I hope I'm pronouncing his name rightly. And I think he was one of the best professors that I had. And he gave us an introductory course about signal processing. And one of the first lectures about Fourier transforms and signal reconstruction, he mentioned that when he first heard those ideas, he had only a rough idea about it. And he also mentioned then that he actually understood those essential ideas in signal processing after 2 years that he actually heard that in classroom. So for me as a naive and a slow learner, that was really good to hear, relaxing to hear, and because some things like take time, and it's okay to not understand everything immediately. I think the most important thing, especially reading scientific papers, etc., is to just be consistent and finding some topic that interests you and maybe be disciplined about it, so that you can take notes and maybe revisit them a couple of times so that you can actually understand some stuff from the material itself. And just
That
another
sounds
small
great.
tip.
Also, just to circle back, sorry,
Right.
just to circle back to a previous point of yours about how we could talk on and on about it, like many aspects of this like more academically maybe, like just to give an example, like one of these sections is on like automatic differentiability and how you can automatically differentiate programs, and that's like a huge topic in itself.
Exactly.
So that's not really something, so that's just like a drop in the whole ocean of differentiable rendering. I mean, like a huge, maybe not just one single drop, but it's just one aspect of how you can derive these equations and how you can make them work actually for your purposes.
I completely agree, and like that's one of the arguments. Like this course notes here that you can see, I think can be a semester-long course as well. Like I think you can arrange a course after the material that has been shown here, starting maybe from physics-based rendering, then differentiation of and then the mathematical tools as well. So
and also this is really advanced in the sense that as you're mentioning it, so this is really like maybe the last lecture of a course on physics-based rendering.
Exactly.
Maybe mention like how we can make this differentiable. So this whole tutorial really assumes like a really good understanding of rendering in general in computer graphics and the different terminologies and equations, and that's really like a preliminary. And
Okay. Actually, before sharing this, I actually also wanted to briefly show the authors themselves quickly. That was a tip. I'm just trying to stop sharing and share another window quickly. I think this is the page. Oh no, this is the article itself. So for people who are interested, we will just give the link in the description as well, but it's basically a website from Zhao and his colleagues that you can access. And basically there's also the video for the course as well. And what I actually wanted to show was this presentation slides, and just quickly show the authors. So the lead author of this course is Shuang Zhao, assistant professor in University of California. Then Wenzel Jakob is from EPFL. He's the lead developer of Mitsuba, and one of the one of the best probably available differentiable renderers out there. And Su Mao Li is, I think, at the moment in USCD as an assistant professor. So with that, you probably remember this slide roughly. Basically, also in my presentation, I kind of the idea originated from this course notes. So basically, in rendering, we have some scene description. The scene description information contains geometry, materials, emitters, camera, etc. And we denote the scene description as a high-dimensional vector of x. And the idea of rendering is the goal is then to map this input into an image, which we denoted as a high-dimensional vector of y. And the idea of inverse rendering then becomes to try to invert this process to acquire scene description information from a given input reference image. Okay, so that's what I wanted to show from the slide. So I'm going to switch to the paper itself. Let me just quickly find it. Okay. So as I mentioned, I'm going to really briefly give an overview. Basically, I think the introduction is one of the best introductions that I read because I think it's, compared to the other sections, much more easy to understand. I think they especially discuss the difficulties really well, especially if you have a naive, at least rough understanding what rendering is capable of. And basically, they immediately begin discussing differentiable rendering and how it's tried to analyze images in an inverse way. And they basically immediately show you an image and what visual effects contains in an image and how it would be difficult to invert that process. So they basically mention that each pixel encodes a complex and messy superposition of different physical effects. And they continue and conclude basically every position is effectively coupled to all other positions through physics of light, and therefore it is not really possible to invert this process of rendering. So then they continue to discuss how renderers try to achieve physics-based or photorealism, and that actually leads to difficulties in a physics-based differentiable rendering because these visual effects such as shadows, interreflection, caustics, they basically revealed this complex radiative coupling between objects. So these effects are crucial for photorealism that we want from a renderer, but they kind of stop us to find a direct inverse of that function. Let's put it that way.
Oh yeah, and they also have a really nice illustration of this kind of coupling because if I'm understanding the terminology right, this pretty much means that it's like intertwined. So if you change one aspect of a scene, it's coupled to many other like pixels, exactly, so to say. So and they also show that like later on this coupling means that you like tweak something and it affects like a lot of other things in the final image.
Exactly.
Right. So that's what this radiative coupling means.
Exactly. Yeah. Okay. So they continue to talk about difficulties, then advantages, then basically the challenges. Maybe the challenges would be interesting to quickly mention. I had a quick note. So the main difficulties or the challenges are the many parameter space, as Barney mentions, how these many parameters are intertwined and makes it difficult to actually achieve this task. The second difficulty was with automatic differentiation, for example, using PyTorch, and how that is kind of poorly suited because of the complexity of light transport, basically. So this light transport leads to unstructured large computation graphs, which makes it difficult to evaluate automatic differentiation techniques. And one of the biggest problems in differentiable rendering is the discontinuities. This can, for example, stem from geometric derivatives like boundaries of objects, etc. For example, computing shadows, etc. So in the last 3-4 years, differentiable rendering papers probably revolved around, especially the theoretical papers, revolved around how to avoid discontinuities that that basically lead to incorrect results to solve the problem of inverse rendering. Yeah, so this is basically introduction for the course notes, and I'm just gonna skip over to the next part. They basically give an overview what the course notes contains, and initially they give a rough focus of the course notes. So basically, they mentioned that we are basically focusing on physics-based techniques and rather than rough approximations. And they may be important to note, by the way. I color-coded the course notes. So the yellow one is mid-priority, the red highlights are high priority, and the blue ones are low priority. So I will be skipping definitely the blue ones.
And also, just while you're mentioning this, like just a meta question, what's the purpose of putting those little notes on the left? So what's your philosophy behind that?
It's rather a rough kind of identification what that paragraph or section contains, but I also did them for today's talk because I kind of wanted to have short sentences as well. But I think it's a good idea in general when you read a paper to just make some small notes maybe about the paragraphs that you read, so that you can. It actually, at least for me, sticks with me after reading it. And especially with highlights, you can then, if you revisit the paper, then you can maybe read the highlights only. So it's kind of a time reduction way, maybe. Yeah, I don't know if it's the best way. How do you guys do actually? Do you also highlight paper?
I feel like first of all, I'm gonna read through, I don't know, some section without highlighting anything to get an overview. And then I try to repeat it until I get an idea of what's the basic point they want to tell me. And yeah, I also like to highlight some stuff because, I mean, sometimes it's difficult if it's always so dense with information because you can't end up highlighting everything. But yeah, sometimes it helps to even reduce the information a bit and focus on what you want to, I don't know, get out of it.
Yeah, true. So just to bounce forward from your last point. So it's really similar for me. So it really depends on how much I would like to take out of the given paper. Like I have different, like I'm trying to develop like different different methods for reading a paper. So one would be just really just skimming through it. So maybe reading the abstract, the introduction, and then the discussion and results. And then, just to get the gist of what it is about, to maybe explore something, then naturally I would like to read through it if it's really relevant for me, and I would like to understand it better. And then there is the most time consuming mode when I also take notes, but it just takes so much time to actually write everything out in each section and to write into notes and maybe even prove the mathematical little like the equations or
Yeah. Okay. Let me continue. Okay, so they continue with motivation and mathematical preliminaries. So I'm going to skip over that. However, if you really want to understand, especially how they kind of find the differentiability of the rendering process, I would definitely recommend reading these sections because they basically provide the reader with a toy example and basically point out what difficulties are there and what do you need to be careful of to basically achieve the task of differentiating the rendering process itself. So maybe small stuff to mention would be that that we talked about automatic differentiation and how it's not really that possible, and they basically lead to incorrect derivatives if you don't really be careful with the discontinuities that the rendering process contains.
Yeah, that's actually really interesting. Just I'm not sure if we should discuss these points as they arise, or maybe at the end. But this is I think this was really an interesting takeaway for me, and I think this also gives rise to many other perspectives on this whole problem. Because what I took away from this part is that the main problem are discontinuities. The example that they have is like you have the three corners of a triangle. And if you move away those points, then naturally the image will change. But at the same time, because the points where the actual changes happen, so the sides of the triangles are actually infinitesimally small. So
exactly.
it's kind of like derivative will be zero. So if you would just like to automate, like also what you mentioned, like the automatic differentiation will give like not good results or like incorrect results because you change the corners of your triangle, so the actual pixels change, but the derivative with respect to the corners of the triangles will be zero. So that was really strange for me.
Yeah, it's an interesting topic because they also talked about this in the video of the course, and I watched that video a couple of times now, also for my work as well, and I think I finally understand what they mean, but it's really hard to put into words, so I don't really know how to say it precisely. But I guess what they're trying to refer is just they when you use especially random sampling, the samples never land in those infinitesimal small boundary areas. And if you actually send a sample into the interior of the triangle, for example, in that case, the derivative will only give you the local change, and that's why you get the zero. However, on the edge, obviously, it changes. Like I think there is a slide also in the course notes.
Yeah, so it's figure 4 actually. I just looked it up. So if you just skip to
okay.
figure 4, I think that really nicely illustrates your point.
Exactly. So yeah, it's kind of like the idea then essentially becomes that they continue to discuss these problems, and the idea then essentially becomes to split the integral into two parts in general, where you integrate or basically the interior and also the boundary in two split two different way basically. So that basically becomes their strategy essentially. So I think they kind of mention it someplace. I had some notes. I think.
So they also mentioned this when they go over to the second chapter or the second part rather, that like okay, until now we've been talking about how to make it work, like how to make this whole concept work, and rather how we can tweak our equations so that even with the discontinuities, our equations make sense. So I think this illustrates it really nicely. And I think it's really interesting that they like pinpoint. I mean, that sounds like so trivial in a sense that like it's discontinuous, and you would like to derivate a function that's discontinuous. So you don't really want to do that. I mean, it's just really interesting that the derivative doesn't really exist there as far as I know.
Yeah, it's really like intuitive. It's not really that intuitive to me as well, but I think they explain the 1D version of that really well. Like there's a piecewise function, and you actually evaluate the derivative of the integral then actually by splitting, basically using Leibniz rule for one-dimensional case where you basically integrate over the interior and the boundary. And that kind of made sense to me as well, but I'm still confused about how that 100% relates to light transport.
Also,
I guess the shadows and the invisibility of objects, I guess, makes it discontinuous. I guess.
So I think a really important concept that they also discuss here is that you actually can't derivate the equation, but you can like the formula, but you can derivate its integral. So they also mentioned this multiple times that even though the actual function is not differentiable, the integral of it can be made differentiable. So I think that's one of the core points.
Exactly, that's also bold here. Right? The integral of rendering is discontinuous and not differentiable, but the integral is actually differentiable. Yeah, that's really basically one of the first things that you should say about physics-based differentiable rendering. Like, this is probably one of the things that should come to your mind if you read the paper. Yeah. Right. Okay, so let me continue. So this is basically in 1D. They basically, as mentioned, find a strategy where they say, using Leibniz rule, to evaluate, to take the derivative of integrals, we basically, for discontinuous integrals, basically, we evaluate on the boundary and the interior. And with that, they switch to multidimensional case. And Leibniz rule for 1D is basically, for multidimensional case, it's then called the Reynolds transport theorem. Maybe Barney can talk about more in detail this time, or maybe next time, because of the fluid your paper about fluid dynamics, and I'm sure you handled this type of stuff in your paper.
Actually, this didn't came up in this context, so maybe I'm just missing some really trivial link, but I haven't come across the Reynolds transport theorem in my work.
Okay, interesting, because they, on the SIGGRAPH course video, they mention this comes up in some of the tasks in fluid dynamics, and how discontinuous integrals may be then solved using Reynolds transport theorem, where you can then split the equation into interior and boundary part. I think one of the papers that we should discuss is yours in the future, so that's kind of a way connection from this today's.
An extremely great connection. I also had some integrals, like totally different integrals.
Yeah.
Well.
Okay, so this is an interesting chapter. I mean, we don't really have too much time left, so I'm gonna have 5 more minutes, and then we can switch to more fun questions again. But this is really an interesting section, and I'm sure they also kind of mention that the performance between rasterization versus ray tracing is a long-standing debate. I think I would really love to read it in the future, because I always find it interesting. And they quick thing to mention, so they give some points. One really interesting thing that I found is that the interior integral and the boundary integral do not need to be computed using the same visibility algorithm. So one can compute the interior integral using rasterization while computing the boundary integral using ray tracing. This sounds really interesting. I guess it's kind of a point that how differentiable rendering is open-ended in the sense of research. So there are a lot of stuff that one can do.
Absolutely. So I would just like to play into this for a bit more. Like, I think it's really interesting that like something that they also say a lot during the course is that everything is an integral. So they really rephrase everything to be an integral essentially. And then actually the like one of the core ideas, I think, is that then okay, and this are the numerical or mathematical techniques that we use to like actually solve these integrals numerically. So to actually get a pixel value or derivative value, and actually at the point where you use the Reynolds transport theorem to have this inside part of your integral and the boundary of your integral, then those just simply become like mathematical problems that you have to solve. So those are just two integrals, and it's well defined. So you have your so the domain of your integration, and then there's just something mathematical that you can solve, and you can use whatever numerical technique, so to say. And
that's kind of a discussion we had last episode, I think, regarding or breaking down equations, so where maybe you can use machine learning to evaluate some part of the equation, and the other part of the equation, then you have to tackle it in some different ways. And I actually, in this course notes as well, they also mentioned the possible use of machine learning to maybe give parts of the equations, but not only for the sense of machine learning, but also one can actually break down the equation such that you can use one type of algorithm for the part of one equation, and the other part of algorithm can be used, for example, with rasterization technique.
Yeah, absolutely. So the last paper that we discussed, I think one of the main takeaways of that was that neural networks are really just universal function approximators. So I think if you just take one of the integrals and say, okay, let's approximate this with a neural network, then that could totally work. So I think that's really the same thing as maybe a generalization of what they are saying here, that naturally you just have two integrals and you can use whatever thing to solve them, because they are not really they're related, but they are just two integrals that you have to solve.
Exactly.
And also I think we will come back to this, but I would also like to linger a bit on the solving the discontinuities aspect and why it's this discontinuous, but I think we will circle back to that later.
Right. Exactly. Let's see how much time we have. Let me check quickly. Okay, let's do a bit more, maybe 5 minutes. I think I said 5 minutes ago, but anyway.
Yeah, sorry, I ruined your 5 minutes, but
no worries. No, please just interrupt me whenever you guys want. So the third chapter is a nice one, especially for people who are interested in physics-based rendering. It's a nice chapter to read. So if you do not have any experience in physics-based rendering, there is obviously a great book called Physically-based Rendering, and there is the new edition of that book. Generally, people from computer graphics call it the Bible. I also have it someplace here. It's also my Bible as well. And also there is the free version online, so it's just a one-click away from you if you are interested in the topics themselves.
I mean, they literally won an Academy Award. So
exactly,
if my memory serves right,
right.
Oh, really?
Yeah, I think so. I think maybe that was the first book or the first academic material that has won an Academy Award, I think, or something along these lines. I'm not sure about the. You literally have it? Oh wow! Is this the new one?
Edition. This is the fourth edition, the new one.
Nice,
Bible.
Nice. Wow.
I definitely recommend checking it out because the third edition of the Bible was really rough to read, but the fourth edition, I think they really managed to explain some of the ideas more in a friendly way, because the third version was really kind of a reading like a source code sometimes, but it got a bit more like a book with the fourth edition. So yeah,
I haven't read it sadly, but because I don't have the book yet. But actually, I think they uploaded 2 chapters available for free to their website. They are on volumetric rendering and two volumetric rendering related chapters. And I actually read those, and I totally agree with you based on these 2 chapters that it really flows well and it makes sense, and it's really nicely laid out.
I kind of bumped into this book last year when I was doing a course about physics-based rendering, and it was at the beginning so hard to read because, again, I was reading the third edition and it was felt like a source code, but after having more experience with the topic itself, it's got much better to read. So that's also maybe it's not a book where you just start to, but you also need to go back sometimes to maybe to repeat some stuff. So it's that kind of book. I guess
I can add a fun a fun fact to it. I just Googled the book, and Jakob Wenzel, one of the 3 authors, is actually one of the authors of today's paper.
Exactly.
So I had no idea.
That's true. Yeah.
Oh, okay.
Yeah. Exactly. He, I think, participate the authors after the 2nd edition, and I think started 2nd edition. They used a part of it. Yeah, and I think also so this book, Physically Based Rendering, has also its own renderer, and initially it looked rather different, but after his participation in the group, the renderer kind of feels more like Mitsuba, which is its own renderer in EPFL. So there's definitely some elements from him that kind of shows in the book and the source code as well. Another maybe small stuff regarding physically based rendering. So on my paper, and I think in general, when you write any scientific paper about physically based rendering or physics-based rendering, well, many of the reviewers kind of pinpoint you that you should either use physics-based rendering or physically based rendering. So my one word to people who are really strict with that word, please just let us write whatever we want. It's not really that important.
I actually never heard this huge distinction. Can you elaborate a bit on this? Like, what's the difference between physics-based and physically
crazy.
based?
So you either use physics-based in the article or physically based, and if you use both in the article, the reviewers write you immediately, please use one and stick with it. I got 2 reviewers from my chess paper. They both wrote, why do you use both? You have to use only one.
Okay, but
and
it's
also
the same
my
thing.
supervisor mentioned the same thing. You should use only one.
Yes, true. But it's the same thing, right? So it's
the same thing.
Oh, okay, yeah, right.
So is it more like a grammar mistake that you use 2 versions of that adjective? Or?
I'm not really sure, to be honest. I think they kind of. I personally feel physics-based sounds better and kind of more accurate, and physically based kind of sounds a bit clumsy to me. But you say something based on physics, I guess. But I don't know. I'm not a native English speaker, so.
Yeah, or maybe you can just put like for the first occurrence like physics-based rendering, and then in parentheses PBR, and then you just use PBR from then on.
Exactly, that's a better. That's a good idea. Okay, let's continue, and okay, I'm just gonna jump out here. So for people who are interested, definitely check out also this section. They basically explain how you can differentiate the rendering algorithm, and again they apply Reynolds theorem to basically split the integrals into 2 parts, where it consists of interior part and the boundary part. They first of all talk about the direct illumination case, then they extend it to differential rendering equation, and then they finally continue with differentiable rendering of participing media, which is a really rough read for me, at least. But I'm not really that good at radiative transport, or volumetric rendered is not really my cup of tea, let's call it that way. So how was it for you, Barney?
Actually, I quite liked it, and I really wanted to like pinpoint something. So I also didn't dive really deep into the mathematics of it, but but what I really liked are these little operators that they use, like these K, P, K, C, and K. Like I think it's like so nice, and I also really like how they like use these little mathematical notations. And I think this is like, I like it so much. It's like mathematical storytelling. Like for example, for equation 23, you see, so that's like an L is a function. So these are like functionals that act on functions.
Right.
And I think it's so nice that they write then the transport operator KT, and I think it's written out so like it's still really complicated. So I'm not saying that it made it like really easy to understand or anything like that. But I think it's like really nice to have these kind of operators. I quite like that. I quite like that.
Normally also like the aggregation of some functions, so you can maybe reparameterize it and use it in a minimal way. But this time I kind of felt like it's maybe too much at one go, but probably because I'm not really that familiar with the
I kind of felt like we are really comfortable with like physically based rendering or physics-based rendering, and then just this is it, and like you know what the symbols mean.
Exactly. But at least they use extinction coefficient with sigma t, I think. Right. I think this was one confusing thing last time. But this is more familiar to me as well.
Yeah, that's really cool. And also what I really like is like I just took some functional analysis course, like one functional analysis course this semester. And I really like because if you have these kind of the notion of these are just functionals and functions, then you have like such a really vast mathematical toolset at your disposal. So at one point they literally just say like, okay, like we have this like some ray space integral, like some integral along the ray that you have for ray tracing, and then okay, we can look at this as a dot product or something like that. Like I don't want to misquote them, but they literally say that it's equation 46.
46. I kind of remember something like that.
It's really cool that these are functions and like the vast mathematical toolset that you can use for these things. So I think it's really cool. So this wasn't really about radiative transport, but about like generally the mathematical grounding that this whole course has. So here you just integrate along the ray. And then they say like this is somehow a type of inner product because it's like You have this notion of inner product between these vectors, where your vectors are functions in this. So this is the whole basis of functional analysis, that your vectors are functions. So then all hell breaks loose. But I mean, this is some of the coolest mathematical stuff that I came across, like this whole notion of just throwing functions around and projecting into function spaces and things like that. I think that's like really, really, really cool. So maybe I was just really excited to see this, and maybe it was there for many other courses that I read. Maybe this is the first time I'm really noticing it, but at the same time, I really like this notion of.
I agree. I think you're right, especially I think so. We can actually skip the previous parts about radiative transfer equation, etc. We suddenly land in this radiative backpropagation, and
that's
section,
really,
I think it's
that's
really
the
great.
backbone.
And the equation that you mentioned also is roughly in these sections. So I think they kind of lay the idea of radiative backpropagation really well, and this section we can really have another episode with this because basically this chapter is actually another paper itself from Nimia David and his colleagues. Really interesting. So basically the rough idea is you are basically emitting differentiable radiance into the scene. This is a really hard idea for me, at least initially. This is differentiable radiance basically is emitted into the scene, and you basically have done 3 different steps how you basically equate the or evaluate the equations.
But the main part, just to not confuse our dear viewers who are still there after all these equations. So the main concept of what you mentioned is that usually for ray tracing you shoot in a ray and then it bounces around. You get a light source, and then you have some contribution for your given pixel or a radiance, or
which is
like somehow calculate
importance, right?
And
importance.
I think it depends on which way you are looking at it, right? So
So
like
if it comes from the light, it's called something else. But I know it, and if it's radiated out of the camera, then it's called importance, if I'm not mistaken. But I might be right.
Yeah, but
Right.
the main idea is that you shoot rays and then you calculate how
right.
much light arrives at your camera. And then the main idea that they build on this really basic concept of ray tracing or rendering is that you can actually shoot out these kind of differentiable components of the ray. So what I understood is that okay, we have this vast tool set of ray tracing and like we know a lot about how to do this thing, and then they give us a tool that like they have some pseudo code or some source code like thing where they literally show that this is really just ray tracing, but you also have a differentiable component. So you propagate with your ray some differentiable component, like some kind of and actually you know what it reminded me of, like yeah, but first just let's could you jump to that pseudo code? Do you know which one I'm referring to?
Really
it's on page 23, so pseudo code and discussion.
Right here, probably adjoint radiance, right?
Yes. So I think this is so sorry if I'm just going all over the place, and this is not something that you had in mind, but I think this was what you mentioned. So you just shoot out a ray, and then you accumulate your adjoint radiance, or is essentially your derivative, and then it's really interesting. And at the same time, you just like you use you sample your BSDF the way that you would do so just in your usual ray tracing setup. And what's really cool for me is that I'm not sure, because here they calculate adjoint radiance, but at the same time I think you can also, while doing the calculation for the adjoint radiance, I think you can also calculate your usual radiance. So actually calculate the color or radiance, and also your adjoint radiance. And what this really reminded me of, but here they show only the calculation of the adjoint radiance. But what this really reminded me of is the notion of dual numbers, or there is another name for them, like mathematically, like dual numbers. When it's essentially like forward. It's the same as for your forward automatic differentiation, where you're keeping track of your, like, dual number is the whole concept is that you have your number, but also the derivative, and then you add together two dual numbers, then or calculating something with your dual numbers. Then while calculating the end result, you're also keeping track of the derivative of that given expression, and this has a mathematical grounding. I'm just looking it up real quick. So yeah, it's Clifford algebra. So dual numbers were introduced by William Clifford in 1873. And so this also has, so it's funny how these are like way back. So this really reminded me of that. Like, but like, I mean, like really, like the bird's eye view for me is that what, like, this is like you're keeping track of what you're calculating, but also what's the derivative of what you're calculating. And to me, this whole adjoint radiance propagation, like having your ray, but that also keeps track where you calculate you also calculate your adjoint radiance, that really rang a bell for me with this notion of dual numbers. But I'm not sure if I'm just way off here. So maybe I'm just too much.
To be honest, I'm not really familiar with them, but to me, it was rather difficult to think about it initially, but afterwards I found the equation. And if you kind of roughly know the rendering equation consists of the emission part and the scattering equation. Basically, the scattering equation gives you information about, or provides you global illuminations, like effects like interreflections, etc. And the emission term is basically comes from the light sources. And anyways, basically the when you differentiate the rendering equation, then you actually get the idea that way. So they basically break it down into three terms. It was actually, the rendering equation had two terms, but the differentiable version of that has three terms now. And they basically tell you, okay, differential radiant is emitted by light sources with differentiable parameters. So differentiable radiance can originate from light sources if you are differentiating that scene parameter. otherwise, differentiable radiance can originate from the material itself if you are differentiated. So this is basically surfaces with differentiable parameters convert ordinary radiance into differentiable radiance, which is kind of a crazy idea, but it kind of helped me to understand, I guess, the idea of providing a differentiable radiance or differentiable emission into the scene. Yeah.
This is
And
quite
another
cool.
important point is that just like normal importance or radiance, differentiable radiance just scatters like normal radiance according to the material properties of the surface. So according to the BSDF, basically, it's kind of really neat. So basically, then you can, as we showed the pseudocode, you can actually emit differentiable radiance and basically trace rays and evaluate differentiability in those places where you have differentiable scene parameters and then actually get the results back accordingly.
Yeah, so just to circle back to what I said about like calculating both at the same time. So they actually don't mention this. So maybe I'm totally off on this one, because I mentioned like for the dual numbers that you're keeping track of your result, and but also the derivative of it. So maybe that's totally a different idea. So here they only focus on the differential term. But what gave me this idea or this connection in my head is that they are using the same tools. So they are essentially the same kind of ray tracing idea of ray tracing, and they are using kind of the same sampling, the BSDF and this whole the whole package. So it's but they calculate like different things at the points of intersections. So but they don't mention calculating both at the same time, I think, or at least I didn't see that or didn't get that way.
Interesting. Yeah, I'm gonna also check out that. Anyways, I think we discussed this quite long, so I think we can kind of stop with this section today, and maybe one day we can talk about this more in detail, especially radiative backpropagation. Do you guys wanna maybe say anything about the course notes or anything about?
I was kind of dropping in some of my points. I still have a couple of points, but if Alessandra would like to go ahead with something, then that's.
No, I just wanted to add that I really appreciate that they have the video, because we were talking about like visual input before, and for me it's a lot easier to watch the video of them explaining it and then come back to the course papers. So I think also like talking about motivating ourselves to read more papers and stuff, I feel like I made the experience that if there's a video existing somewhere where they, I don't know, talk about it at some seminar or something, for me it's so much easier to get into reading papers.
Yeah, absolutely. Sometimes I learned it way too late after reading a paper that they actually have like their presentation uploaded, which is really like the condensed gist of the paper. So that's so nice. And sometimes I already like processed the paper and took notes and everything, and then I found that, oh my god, they have such a nice introduction, like a video in a video format, and I should have seen this. Like so since then I'm always trying to find some recording of the presentation or something to get the gist of but sometimes it's not uploaded. But yeah, I think also the video format is more polished, I think. So I think they put they also put a lot of effort into this one, but I think that was the course. So this is kind of like not really a publication, but like some notes.
Yeah, true. I definitely agree with that. And I guess, but the one reason why I wanted to talk about this course notes before actually talk about radiative backpropagation, there are not really there isn't really a material where you can start with differentiable rendering, and this is probably the best place to start, because they try to at least combine some of the approaches that differentiable rendering in the last 5-6 years
also because like as we mentioned, there are so many topics involved, and all of these are evolving all the time. And here they are kind of condensing multiple papers, and they're also citing each of them. But if you look at either one of these individual papers, then I think it's really hard to see the big picture of differentiable rendering, and that will be just some small component of the whole big picture, and I think it's easy to get lost in the given detail. But at the same time, like, research is all about the little details.
That's also true.
Some of the time. Yeah.
Right, that's also a good point.
But for sure, like, it's much less polished than like a proper publication, even though it's really well written and everything. But they naturally have like little to be done sections, and I don't know, like minor typos and like little things. But also it's really beautifully edited.
I'm not really surprised that you found the typos.
Oh, no, I scared to even mention that. No, I didn't find
Yeah, definitely. I would agree, and I would also say, if you're gonna somehow, saying now to the listeners, if we have any, definitely, if you're gonna read this, check out the video and kind of combine both. Then it's much easier to grasp the ideas. Yeah,
absolutely. And also I have like a couple of points that are really interesting for me. So one of them is about this whole. So at one point in the video, they mentioned that this whole concept that we're introducing here is independent of the way we store our 3D data. So they say that you could use. Do you remember that part? Like, they say that, okay, we will focus on mesh-based, and so you have vertices, faces, and edges and stuff. But you could also have any other kind of scene description, and it wouldn't matter which one you use.
Right.
And they even mentioned that you could even have like some fractals or something. But yeah, then the boundaries are a bit. I'm not sure if that's well defined, or they say something like this during the video.
That's true, because I think, if I remember correctly, the idea, I guess, is to find a generic way to differentiate, I guess, the rendering process itself, I guess.
Yeah, but what's really interesting for me is I'm not really sure if this is the case, because maybe this is like an edge case, and but naturally, like NeRFs or neuroradiance fields come to mind, and those are literally scene description. So they literally store. They have an X, Y, Z, and like θ1, θ2, or like 2 degrees of view directions. And those are also a scene description, in the sense that they store. They are a function of your what is in your scene. But at the same time, there with NeRFs, you don't really have like much of these problems that the whole course is about solving. So because then you have, like, you're continuous in all of your parameters. So you're continuous in X, Y, Z, and in your 2 view directions too. So you're not really constrained by the discontinuities in your scene. And I was really thinking about that. Like, it's so easy and even trivial to like differentiate a scene depicted by NeRFs, because then you just tweak your theta parameters of your neural networks, and then you have your scene description, and then you're continuous in all of your parameters.
I guess it originates these discontinuities mainly because of the assumptions that we have, especially in physics-based rendering, such as steady state assumption of light and how it propagates. I guess that's basically the main reason, and one of the reasons I probably also Monte Carlo rendering. So I'm not really sure whether there is a random sampling involved in an approach like NeRF, or what's the actually frame arching, I think, if I'm not mistaken. So I guess the main difference, especially in the physics-based differentiable rendering part, is that we are trying to use or try to solve the integrals using Monte Carlo rendering, where where our approach basically is consistent and unbiased. And I'm not really sure whether ray marching, I'm not really familiar whether whether that approach is biased or unbiased or consistent with statistically.
Yeah, that's right. But it doesn't really matter, I think, because it's just the description of your scene. So it just encodes. So kind of the way that they write the whole run. Yeah, but maybe it's not really suitable for your user rendering, because then you would also like to have like a proper 3D model extracted from your NeRFs, and then you have like different problems. So that's absolutely true. But it's really like I think it's really interesting because like naturally like the whole research community kind of has been going crazy about NeRFs, and I think they really like really trivialize some of these problems, so to say, because and then I read or like read some papers where they would like to have like some differentiability with respect to a 3D model or with respect to like scene parameters and anything. When that's a NeRF, then that's trivially doable because your NeRF is just like a neural network, which is of course differentiable. And have you read the DreamFusion paper by any chance?
Nope.
It's actually quite cool. It's quite cool. So what they do there is they do like text to 3D using 2D diffusion. So what they do is you input some text and then they output a 3D model of.
I think Wenzel in the presentation also talks about some of the approach. Maybe that would be a hint to answer one of the questions, but I'm not really sure. I think it's a good question that you are asking. I'm not really sure, to be honest. But maybe Wenzel might be answering some, at least giving a hint why it is actually relevant in this case. But yeah. Really
but at the same time, I think the NeRF paper came out in 2020, so the same year as this, or was it in 20? I think it was in 2020.
2020, and this is also 2020, but differentiable rendering also continues. Like there were a lot of papers after 2020 as well, after NeRFs. So, yeah.
Yeah, right.
I don't know.
So this is the DreamFusion text to 3D using 2D diffusion paper, and so naturally the 3D model. So if you go to the project page, they have much better animations and stuff. But for example, this is an orangutan making a clay ball on a throwing wheel, so it's kind of cool. And these 3D models are NeRFs essentially. So it's really cool, like Corgi taking a selfie, like it's so cool. And what really the
from somewhere.
figure.
But I didn't read the paper.
Oh, really?
Yeah, I don't know. Came up somewhere.
Oh, maybe the 2-minute papers channel. If you were watching that, or
I don't know. Or maybe you send it to us at some point. This could also be the case.
Oh yeah, that could be. So here, like naturally, this is not the paper we are discussing, but just the big picture of it. Like literally, what they do is they have some 3D model as described by a NeRF, and then they compare it against some result that they would like to see, and then the whole kind of not really differentiable rendering, but the whole kind of concept to like it's kind of differentiable rendering that they say just that we backpropagate onto the NeRF weights, which are these theta weights of your MLP, or also called a NeRF. So naturally NeRFs are really simple MLPs. And it's so cool that like the whole differentiable rendering component of this paper is like backpropagating onto NeRF weights. And as far as I know, like everything in this figure is differentiable. And I think that's just really cool because and it's really kind of
definitely like NeRF approach definitely probably will be more usable in the future, I think, compared to use of physics-based differentiable rendering. Like, to my understanding, it's more for a task, for a more specific task where you definitely want to understand the underlying equations and underlying processes that involve the light transport. And I guess with NeRFs, you can basically roughly get the result immediately almost, especially these days. So
yeah, that's true. And then at the same time, also like NeRFs use this kind of volumetric rendering concept because they have this yeah. So it's essentially volumetric rendering the way you use NeRFs.
They use ray marching, right? Is it
you literally shoot rays into your scene, and then you add together the little, like, you just use volumetric ray tracing essentially, or volumetric rendering for NeRFs. So there is also kind of physical bias there, as far as I'm using the term correctly. But yeah. So anyway, I think it's really interesting, and it would have been fun to have this course after the year NeRFs came out. But yeah. We will see.
I have a small thing about that. You can next month. You're gonna be in SIGGRAPH, I think, in Los Angeles, and you can ask Wenzel. You can bother him with this question.
Yeah, I will walk up to him and ask, hey, man. Yeah, I mean, I'm really looking forward to chatting with people on SIGGRAPH. Yeah, that's for sure. And also, like, one thing that really blew my mind, like an idea that I wrote down, is this is just like a really an offhand comment that they have, that you could use these concepts for hand-drawn ground truth optimize. Like your ground truth could be hand-drawn, and they don't really elaborate on this in their video, but I think that is just so cool. Like, just imagine you have a scene in a movie or in an animated movie or something, and then you take a paper and then you just sketch some lighting, like you would like to have like a green light from the left and the blue light from the right, and you do nothing else. You just pull up like a paper or Photoshop, whatever, and then you just write in some colors, and then you optimize your scene. But naturally, it won't really disturb or destroy your scene because there is like an existing grounding in how much light sources you allow the scene to have. So but it can tweak the position and color and everything else of the scene, or even or like whatever parameters of the scene, to give you a feeling. But at the same time, you just drew some some lighting.
Yeah, I know the video.
The page.
It's a really cool video. Yeah, where you just let me quickly find if I can.
Oh, there's a video of this.
There's a video of this.
Oh, cool,
they discuss it in one of the papers. I think it could be a paper that for Mitsuba 2. This is the differentiable render.
Okay, I haven't seen that. They just mentioned this really offhand.
Yeah, there's a video. Course. I will definitely find that out and give it in the description to this video.
Cool. Yeah,
it's a really cool video.
Yeah, I can just imagine, like, that could be such a nice workflow. Like, just imagine you're working on some movie and you would like the lighting or whatever to have kind of an atmosphere. You'd like to have some cloud or something, and then you just like draw it in Photoshop or something. Like an artist can draw it and just drop it into differentiable rendering, and that's so cool.
But the main difficulty, at least from my experience with differentiable renderers, you, at least for this type of scenes, you need to have an initial state. And that could be sometimes difficult to find the best initial state so that you don't really land in a local minima. And then you don't really get the result that you wanted.
Also, it really depends on, I think, on what you're optimizing for, because naturally, if you're optimizing for all the vertices of, I don't know, like an object with 6 million vertices or something, then naturally it's kind of funky. But at the same time, if you have like an XYZ position of a light source, for example, or like six positions of 2 light sources or something, so like 2 times XYZ for 2 light sources, then I think that might work better. But at the same time, but I think that's much more easier to kind of start out, or to have a good optimization.
Yeah, I'm just gonna try to find a small video that I had, because I'm at the moment working on differentiable renderer where we try to optimize shapes that we photographed in real world. Let me try to find it if I can. It's definitely tricky because the objects itself in virtual world has a lot of triangles, but you just like the algorithm itself developed so well, it's just not that difficult anymore. Because 2 years ago it was too difficult memory-wise to do that, but I think it's getting better. Do you guys have any additional stuff that you want to add about?
I mean, we're still waiting for your question, right?
Right.
Yeah, that's true.
Okay.
Yeah, that's true. Yeah, that's true.
Okay, just a second. I will.
Yeah.
Then before doing that, I'm actually trying to find out this mini video in the meantime, because it's kind of looking cool. History.
I'm actually at
just a second.
On the DreamFusion website, because
Right.
I can't get it out of my head. Where have I seen those pictures? I don't know. But I think you can try this out directly on their website.
Yeah,
if I'm not
I think
mistaken.
they really went some rounds around like many news outlets and YouTube videos at the time DreamFusion came out. So I wouldn't be surprised if you just saw it on, I don't know, Twitter or I don't know, even a Facebook feed or something like that, just pretty randomly, because I think they really went some rounds. I mean, just one idea that I still had that was like really cool for me to make another connection is that they refer to the adjoint sensitivity method, and where you have a problem where you have a time dimension and then ordinary differential equation or something like that. And it's really interesting, and that they cited this as the motivation for their adjoint rendering concepts, and that was really interesting for me because I'm not sure if you know them, but at the University of Washington you have Steve Brunton, Professor Steve Brunton, and also Professor Nathan Kutz, who are doing lots of like optimal control theory and control theory, and they just released a new edition of their data-driven computing or data-driven scientific computing or something like this, which is like one of the coolest books I've read on kind of these optimization topics. And they also have, and also it's not really from them, but there was also a roadmap, or which is kind of like a book, that is the control theory roadmap for the next 10 years or something. And it's really interesting because I never really came across this whole concept of control theory, but it's so far-reaching, and it really comes up because essentially this is what you would like. We'd like to control some system, some static or dynamic system, and this is really interesting. Like you can either have an actual time dimension where you would like to optimize some process, I don't know, fluid flow, even an ODE, PD, like partial differential equation or an ordinary differential equation, where you have a literal time dimension. But at the same time, you have some of these like steady states problems or essentially also like, or even also ray tracing, where you have a virtual time dimension, so to say, because you can think about your whole problem where you have your rays as it kind of could be thought of as a virtual time dimension. And it's just really interesting to me to kind of have them also refer to this in the Physics-based Differentiable Rendering course, and they cite an older publication on
ODEs, I think, right?
Yeah. And the adjoint sensitivity method, which is essentially automatic differentiation. So it's kind of like backpropagation.
I think the idea actually originates from them, that this ODE paper that you mentioned from 60s, I think a Russian scientist, basically gives their initial approach, which is kind of crazy, right? Because you're writing a paper in 2020 and suddenly you just find yourself reading a paper from 60s and it just shoots perfectly for the task.
I just love how mathematics never get old. It's just wonderful. It's just wonderful. So anyway, I just wanted to mention this because I think it's really interesting.
That's a good point.
How this is like a control theory problem. This what like you have some system and you would like to find some optimal control of that system, and in this case our system is kind of like a rendering frame.
I think it's Portiagin 67, something like that. But I will definitely give it in the description.
Yeah, it's something like that.
Portiagin. Okay. Okay. Let's finish it.
Yeah, but this was kind of like a wrapping up. This was kind of the start of the wrapping up.
Let me finish. Let's then finish with my question. What's the most annoying thing to you guys that originates from computer graphics? This podcast.
It's not an easy question.
I mean, yeah.
No, I'm just thinking.
I personally can say really quickly. I'm not really familiar actually with rasterization techniques, etc. So I'm kind of trying to learn about more. And I started with Web GPU, and it's sometimes so annoying how you have to debug and how you can't actually debug. It's just headache. So to me, as a normal C++ developer and worked with rendering, etc. as well, it's just annoying, like really annoying sometimes if things don't go well.
But you saying that C++ is like the language where it's so easy to do everything, where nothing goes wrong. I think some people are just like screaming and turning off the podcast right now.
Right.
Yes.
But at least you can debug it. Yeah.
So Alessandra, debugging also for you, or?
I feel like I might be one of those people that would have been like, what are you saying? Because in my bachelor studies, I never had to do C++. And I first had to deal with it through, I think it was like what's it called?
You have Web GPU, but we also have WebGL. So those are two different things.
I think it's WebGL or something. I don't know.
Yeah, I think it is WebGL. I think because WebGL is really new, so I don't think they wrote the studio fans that.
And I also had to deal with the debug. Yeah, like compiling and debugging and like. I don't know. So that was also annoying for me, but for a different reason, because I've never done C++. This was a weird introduction to it.
So kind of when you have the whole mathematics worked out and you have the concepts and you know what you want to do and everything that's up between you and the
And I'm used to like, I don't know, Python or JavaScript, so I'm like, okay, how do I run this now?
Yeah.
I think also we have some people that will turn off the podcast now.
Yeah, that's true. So,
I mean, it's so easy nowadays, like using Python or JavaScript. It's just like if you still want to write a really reliable program, especially for a program if you want to build on a computer, then C++ is probably the right way to go. But otherwise, why do you wanna deal with C++ and get a headache?
Yeah. I think I have to cite some similar kind of technological aspect, but nothing specific. But I mean, like when you have like all the different frameworks and like for example like Apple dropped support of OpenGL, and I had my stuff in OpenGL, but then I bought a MacBook and I mean, I can kind of make it work, and you have some I don't know, like some kind of version that you have some kind of like plug that you can use somehow, but then you would, but I think we are really kind of spoiled because in a sense, because we have so many beautiful things like also, for example, Tai Chi or PyTorch, and like for example Tai Chi, what they do is they kind of do like a whole another level of abstraction above the concrete implementation that so you kind of it's kind of, it has a Python front end, but it could have like a JavaScript front end or whatever. You kind of write your Tai Chi kernels, and you can choose what you would like to compile it to. So you can compile it to the CPU or different or even Vulkan or WebGL or whatever, and even to mobile devices, and so it's really nice in this sense. So it's kind of gets these technical details away, but at the same time it doesn't really always work. So for like there are so many little things that just don't work, and it's and also like you can also have an abstraction beyond like for example, I think Keras just released a PyTorch backend, I think. So like Keras was exclusive for TensorFlow, I think, and I think quite recently they just released a statement or even a product. I'm not sure. But they stated that you can use PyTorch with Keras or something like that. So I think there is so hard to keep track of these, and this kind of is my problem. Like there are so many new things and so many new technologies, and then you also have this kind of I don't know, like this kind of dynamic between companies and what they support and what they drop support of. And we see this all. I think maybe that but when I can't just concentrate on the research or the actual implementation, I would just like to see that really cool thing in action. But then I have to spend like hours on like how do I make it work? And then, how do I make it work on your laptop and your laptop and. Yeah, like all of my respect goes out. Yeah, all of my respect goes out to people who are working on stuff that really abstracts this away and gives you a tool that you can use to just go out and do your stuff and be happy about it and have some beautiful visual stuff.
I definitely agree on you with that, because I had the same experience, especially after reading some papers. Sometimes you want to check out their code, etc. But it doesn't build, so it's just so annoying sometimes.
Because it used like Python 3.7, but you are on 3.9 or 3.11, and it used like that and that. It's just I totally get it. And you don't have the proper GPUs, and it's just one little part that you have to modify to make it work on CPU. But then you don't have enough. I don't know what, and it's just a mess. And and also, for example, like all my respect goes out to like people who are working on these kinds of problems. For example, at Unity, I'm not sure if you used Unity, but there you have the option to export your project to so many different platforms. Like you can export it to web browser, to mobile devices, and I mean, I just can't even imagine the amount of work and like sweat and blood that goes into like making your Unity project.
The engineering part of it, it's like we kind of are more interested in the research side of it, but there is a huge amount of engineering parts in these type of projects, like the interfaces that you need to build and how tricky they are and how the technology evolves, and you can't really maybe sometimes meet the requirements that comes at you. So it's just really also hats off to them from my side as well. It's just a headache. I know it also from my work, because different stakeholders want different stuff. So it's just sometimes I want to kill you. But anyways. Okay. I guess that's it for our second episode. Thank you very much for joining me. I will now stop the recording.
Yeah, thank you, and hope to see you again. It was
me too.
Bye.
Bye.